Hi, everyone. Thank you for joining us today. We are excited to share our story of how we created an API definition repository for OpenSearch, a project that started with frustration and ended with community-led transformation for us. Right. So I'm Sachet Alva. I'm an software development manager at Amazon OpenSearch.
And I'm Pranav Garg. I'm a software development engineer, also at Amazon OpenSearch.
So together we'll walk you through how we took OpenSearch's APIs and created a structured API definition framework that's now driving client generation, documentation, and community collaboration, basically. So Pranav, let's dive in.
Thanks, Sachet. Hey, everyone. Now, you might think that this is a presentation about API definitions, and that might be it, but it's not. Honestly, it's a personal story. It's a story that transcends organizations within Amazon. It has all the human emotions, anger, sadness, a hope for change, making that change, and finally redemption. Now, this is also a story about how you can propose your own ideas for an open source project. This is a story of the OpenSearch API specification repository. So naturally, it has these 3 acts and a prologue and an epilogue. Now, you might have heard of this project if you attended Takeshi's talk yesterday about client generation, or if you attended the talk from Uber where they talked about the protobuf generation right before us. At the very end, we'll be taking questions and answers, so please write them down. And let's get started. So how did we get over here? See, in the beginning, before the Earth was formed, there was nothing. It was an endless void and just time. A few unimportant things like evolution, fire, and wheel happened in between. And then suddenly, the most important thing happened. There was leucine. After the leucine came the predecessor to OpenSearch. Now, this was a complex beast. It did not play by any of the rules. There were APIs which were GET, but they had payloads. They were not idempotent, and there was no formal API contracts. Now, this is reasonable, right? Because the project, it grew rapidly. It became like a Swiss Army knife, and API, it took a backseat. It grew large, and it grew fast. Licenses were changed, and finally, OpenSearch was born. Now, OpenSearch, it boasted more than 200 APIs, but there was no API definition. Wait, hold on. What is an API definition? Well, API definition, API specification, interface definition, that's pretty much all the same. Now, whenever you are creating a service, you would want external callers to call it, right? Else, what's the point? These callers can be other services, it can be your front end, or it can be your end users. Now, there needs to be a way for them to know what is the HTTP methods that you have implemented, what is the input structure they have implemented, what's the output, what are the auth types. Now, one way to do this is I've created the service, I'll go ahead and write the documentation. You read that documentation, and you create your POJOs or whatever classes you're using at your end. This is not an error-proof approach, right? So that's where your API definition comes in. It provides you with a formal API contract that contains all of this information. And irrespective of your backend, since data is transferred over wire, mostly in a string format. So formally, you can say it's a backend agnostic way where data is sent as a string between services. Now, there are plenty of different languages you can use to describe your API definition. You can use OpenAPI, you can use RAML, you can use Smithy. But let's take a look at an example. So this particular example is an OpenAPI. I've created this sample API service, which has an introduce method. Now, the introduce method has an input, which is mentioned over here, and outputs based on your HTTP code. This is where we have actually defined what your object should look like. So your input object is going to have 2 fields, name and age. The first is of a type string. The second one is of a type integer. Similarly, you have the output. On the right side, you can the left side, you can see what the JSON is going to look like over the wire. Great. So now we know what our API service expects as an input, what it expects as an output, and what the API endpoint is. Now, what exactly is the use of this API definition? As we said before, the contracts, they ensure that there is no uncertainty between the caller and the service. So when we follow an API-first approach, we first create these contracts. We use these contracts to generate your classes that we use to serialize and deserialize your inputs and outputs within your service. This leads to a complete coupling between your API contract and your service. Now, whenever your client, your end user is going to call your service, they're also going to use these contracts. So there's no scope of any ambiguity over there. You can also use it for documentation generation, creation of mock servers, automated testing, metrics, etc. OpenSearch had no API contracts to use at all. You had to go through the documentation, generate your own clients, and give JSON strings as inputs and outputs. All the documentation was created and maintained manually as well. Now, remember I told you this is a personal story? See, a few years back, a Gleamy intern joined Amazon. That was me. I was the Gleamy intern. But yeah, as part of my internship, I had to learn the best principles when it came to coding, cloud architecture, design patterns, microservices, clean coding, integration testing, and all of that. Towards the end of my internship, just for brownie points, I had to implement a search solution to the data ingestion suite I had created. Of course, I was excited. Search is a fundamental computer science problem, right? But that excitement was going to turn into misery soon, because I took API definition for granted, right? I mean, you have this search engine that you're going to call, and you're going to get the outputs. At that point of time, client which was used with the predecessor was quite famous. It was called as a Jest client. Jest client had no POJOs. You would go ahead, call a particular endpoint with a string input, and you'll get a string output. So I thought it was a joke, but my mentor clarified it's a jest, but all right, makes sense. So anyway, this was the code I ended up writing. It's a representation of that. It's string substitution. It's string substitution prone to errors. I could not ship it to production, so I put lipstick over the pig and wrote it to look much better, but underneath it was the same. It went against all the coding principles I had learned so far, but anyway, I pushed it to prod, I got an offer, and I worked at Amazon for 2 years. The code scarred me for life, though. Every once in a while, a junior would come up to me and ask that, what exactly have you written over here? My answer would mostly be a regret, but oh well. So soon I found a spark of hope. You see, after working at retail side of Amazon for 2 years, I decided to move to AWS and saw an opportunity at AWS OpenSearch. My wounds, they were burning a bit. But here is the twist of fate. That's where I met Sachet. And Sachet was facing a similar problem. Now, we had to write some tests which required some fuzzing for the OpenSearch data plane. That required an API contract, but there was none. So what Sachet decided to do was that he tried to create the closest approximation he can get to an API contract. Instead of an API-first approach, he decided to create an API contract after the service was already created, years and years down the line. This is exactly what we needed, and that was our eureka moment. As mentioned before, usually you write the API contract first, use that to generate classes, and then use it to the service, but that was not an option with OpenSearch. So we decided to do it the other way around. Still better than nothing, right? Now, OpenSearch, it was created recently, and AWS was spearheading this particular initiative. So we discussed this idea amongst our colleagues, and we got a unanimous consensus. But something as fundamental as API contract had to be available, right? So the first thing that we did was look up online. At that time, we did not have deep research. So of course, it was the old-fashioned way, Googling and searching multiple GitHub repositories. We saw that there were a few independent attempts by some people which were abandoned because they did not have any community development on that. We also saw that OpenSearch itself tried to do this in a different way multiple times. That would include REST specifications for integration testing and REST specifications for generation of client. but nothing as formal as an API definition. We also saw that a lot of requests were created and prematurely closed. So this problem existed, and it was an actual community pain point. So what we needed to do was to create a proof of concept. Now, we are just defining an API contract. I can do anything by that. But we needed to prove utility to the community if we wanted to move forward to this. For us, it was just integration testing. So what we tried to do was generate clients for a few APIs which we had created. These particular clients were, These particular clients, they helped us discover potential issues such as the unavailability of untagged unions and the same API having the same fields in both the URI and the query parameters. This helped us quite a lot to know what exactly we'll be facing when we'll be doing the actual implementation. After this was done, we created a plan of action that required choosing the correct tools. For us, it was Smithy versus OpenAPI. Sachet is going to talk about that. We selected an initial set of 15 APIs, all with different payloads, different functions, and different implementations, just to make sure that we have a proof of concept outside our way, and then community has something that they can look into and adapt onto their own. Finally, we wanted to have an integration test framework. As we said, our API contract is a model, and all models are wrong, but some models are less wrong than others. So just to ensure that the API contract meets what is the actual reality, we decided to create an integration test framework. After we had all of this in place, we reached out to our leadership. They agreed and had complete consensus. So we thought we are good to go. But there was an issue. This was an open source project, so we needed to get community approval. We put all of this inside a RFC and published it. After a few weeks of discussion, we were finally able to get an approval for this. And this was the RFC that was published, and the repository was born. Now, Sachet is going to talk about the implementation.
Thanks, Pranav. Moving on to the implementation. So let's start with the technical challenges. Like Pranav mentioned, we had our RFC published, it was approved, and we were ready to dive in. But we quickly discovered something. We had signed up to be essentially digital archaeologists. We had to excavate through layers of code history to understand how the API behaves and how we should model it. Now, OpenSearch's APIs had evolved organically over years, crafted by hundreds of contributors. Each layer of code told a story of its time. Features were added by different teams, workarounds that became permanent, and behaviors that made perfect sense, only if you knew the actual context from 5 years back. Right? So many critical behaviors weren't documented anywhere, except maybe in some code comments, and some of them not even in comments, basically. So we found ourselves piecing together true API behavior by going through commit histories, test cases, and scattered documentation. Our challenge was not designing APIs. It was accurately capturing what actually existed, quirks and all. We couldn't simply create what we thought the API should be. Instead, we had to document what it actually was, and we had to respect backward compatibility. Now, this archaeological expedition took us through pull requests from years ago, forum discussions, and even debugging sessions to understand why certain parameters behave the way they do. The deeper we dug, more we discovered just how intricate these APIs had become over time. Now, this is an actual picture of us. This is how we were when we started. We had no idea what we were doing. So we needed a plan of action. To make sense of it, we came up with a systematic approach. For each API, we started with deep code analysis, where we actually went through the code and found how the request is handled for each parameter type. For example, we found in certain cases that serialization and deserialization of input-output was happening at different layers of code. Some API parameters were being parsed in the initial REST handler itself, whereas some of the remaining parameters were parsed somewhere down the line. And this was not expected. I mean, you expect the entire parameters to be parsed at the beginning itself, right? But we had to go through multiple layers to actually make sense of some of these APIs. Now, documentation review was next. For every API, we had to also go and figure out if the documentation calls out some parameters. And if there's any discrepancies, we had to figure out if code matches it. Then we had test cases, and test cases were invaluable. Basically, these were the one place where we could make out that what the actual behavior of an API is compared to what we thought it should be. Right? Finally, we also recognized early that we couldn't do this in isolation. We needed communities cooperation, right? And many members of the community, for example, were better understanding APIs, and it helped us capture some of the edge cases early on. Now, this was not a one-and-done process. We refined our definitions iteratively as we uncovered more information and received more feedback. This approach helped us navigate through the complexities. Now, talking about the tools of trade, right? So Smithy became our foundation for API modeling. It provided strong typing and robust validation. We'll cover more details about this in the next slide. Another important decision that we took early on was enabling OpenAPI as a compile time output of Smithy builds. Now, this gave us the flexibility to support various ecosystems and ensure our work would be broadly compatible. We wanted to leverage the best of both worlds, the mature ecosystem of OpenAPI, along with the powerful modeling capabilities of Smithy. This particular approach paid dividends as the project has grown. To verify our work, we developed scripts that tested our definitions against real-world API behavior using a testing setup that we built using Dread. Now, Dread is basically an HTTP API testing framework which validates an API model against actual behavior by automatically executing calls to the backend service. We created a GitHub action which spun up a Docker container for OpenSearch. It then used the OpenAPI specification from the model to automatically execute tests against the OpenSearch endpoint using examples specified in the model itself. This ensured that we weren't missing critical functionality or misinterpreting behaviors, and ensured that all commits to the repo were thoroughly tested. Now, this brings us to the bigger question, like why Smithy? When starting with this project, our first major decision was this, and we had to choose the right interface definition language. We had two main contenders, like Pranav mentioned. We had Smithy and we had OpenAPI. Smithy, even though it was a newer modeling language, it won our initial evaluation for several key reasons. Firstly, it offered a very intuitive syntax that's very close to programming language. I'll show you an example in the next slides. But this made defining complex API definitions much more easier and much more readable. The strong typing system of Smithy meant that we could catch inconsistency in the build process itself. Similarly, the validation that was built in Smithy helped us catch issues early. We valued that Smithy was basically protocol agnostic, and it was highly extensible. And both of these qualities were what we were looking for when we want to model an API definition for a service like OpenSearch retroactively. And critically, one of the more important ones was that it can generate OpenAPI specifications. So we were not stuck with Smithy. We were open, and we had options to move to OpenAPI whenever we needed. One more thing was its documentation capability, which meant that we could enrich the API definitions by putting rich documentation right next to it. After months of work, we had our first set of API definitions ready for prime time. Now, this was a significant milestone for us, moving from concept to reality. These APIs we organized logically. We grouped them based on operation names and HTTP methods. For example, here, what you're seeing is the index level operations, for example, went inside the indices directory, which in turn contained one directory per API endpoint. Now, one of the first experiments that we did early on was generating human-readable documentation using the Smithy API definitions. We also experimented generating client code, and for that, we used OpenAPI generators. We also used client code generators by Smithy, and all of them worked. Now, this gave us practical proof that our concept actually worked, and that investment would deliver real value for developers and users. Next, let's take a look at the initial API model that we merged. I'll walk you through the API definition over here. So what you see here is basically an HTTP decorator which specifies the behavior of an operation. Here we say that it's a post method operation. And this is for index level search, where index is the HTTP label in that URI. Next, we have a documentation annotation. This is basically where we put the documentation text. This is followed by the operation definition itself. Naming convention, again, here was the HTTP method name followed by the operation name. Internally, it contains two fields, input and output. The input field specifies the input request structure, and the response field is mentioned in the output structure. So, and here is an example of input and output response structures. So, starting with the request, here we have HTTP label annotation and a required annotation on top of the index name. So, this is required for the URI. Next, we have some query parameters. We included only a couple of them here, but the actual search request has much more. And finally, we have the request body parameters. Similarly, we have the response structure on the side. So now, if you take a look at this, like we said earlier, this basically what you can notice here is that each of these fields have a data type associated. So it can be a primitive type like Boolean or integer. We can also have complex types like time or hits metadata. Smithy's code-like modeling approach was a key reason for us to choose Smithy. It offered a familiar paradigm for developers with structures, annotations, type checking. This mirrored what we do every day. The build time validation was particularly valuable, catching inconsistencies early before they became a problem in our production. Also, like I said, we appreciated extensibility that Smithy provided. This allowed us to represent the diverse patterns we encountered across OpenSearch APIs. Its support for distributing models across multiple files was also equally important for us. We could logically separate our API definitions so that it's easier to read or find out when we needed one. And finally, something that might seem small, but it was incredibly valuable. Smithy supports inline comments. So you see comments on the definitions on these request response bodies. This allowed us to document our reasoning directly alongside the model definitions, preserving some context that would otherwise be lost. What came next? So when we first released our API definitions, we were truly proud of our work. Client library maintainers also quickly showed interest. They too had battled with string-based request bodies and appreciated the structured approach. After defining the initial set of APIs, our team's focus shifted to other projects. We handed over the repository to the community. While additional APIs were being added gradually, the contributions didn't accelerate as we had hoped. In retrospect, this was not surprising. Modeling APIs for an existing API service isn't the most exciting work. And learning curve for Smithy presented a real barrier. Many developers were already familiar with OpenAPI, making Smithy an additional skill they had to acquire. Now, this led to a thoughtful community proposal to switch completely from Smithy to OpenAPI. And what followed exemplified the beauty of open source. A robust, transparent debate weighing the technical merits of both approaches. After considering all perspectives, community decided to adopt OpenAPI. Thankfully, we had included OpenAPI specification generation in our Smithy builds. So this made the transition relatively smooth. We already had the OpenAPI models to start off our new OpenAPI repository. Right? Once completed, we witnessed a remarkable shift. Community engagement increased, contributions accelerated, and our initiative truly became community-owned. This evolution also enabled the creation of a Swagger Explorer, where developers could interactively view and test APIs. Finally, this taught us a valuable lesson. Sometimes the best technical decision is the one that removes barriers and empowers your community. Some lessons that we learned on the way. These apply well beyond API definitions. We discovered the power of starting small. Selecting a subset of APIs representing our diverse use case, we could dig into their peculiarities and build confidence in our approach. This focus scope helped us demonstrate value quickly while build momentum and even though the task was overwhelming, we were able to manage it. We learned, sometimes painfully, that automation isn't just nice to have, it's absolutely essential. Our initial testing automation, comparing API models against running OpenSearch instances, saved countless hours. Later, some teams created tools to generate OpenAPI templates from existing definitions as well. The OpenSearch code base humbled us regularly with its unexpected patterns, inputs being deserialized across multiple layers, endpoints supporting different methods with the same behavior, and many other complexities. Now, these surprises showed us how software grows more intricate over the years, develops quirks that don't fit neatly into standard patterns. But it works. We embraced a philosophy that became our mantra. Perfect is the enemy of good. This pragmatic approach kept us moving forward when faced with challenging edge cases. And perhaps the most important thing that we learned was that true success sometimes means letting go. It's like watching a child take their first steps, seeing the community embrace and transform our initial work into something greater than what we imagined was the most rewarding outcome of them all. Let's quickly take a look at the numbers. We have made substantial progress. To this repository, there are more than 60 community contributors who have demonstrated their interest in the API standardization. As per the latest coverage report, 663 OpenSearch endpoints have been already defined, and this covers more than 65% of the total API surface which is available. There are 5 different client libraries which are now leveraging these definitions, ensuring consistency across languages. There are 2 more in progress. While we're proud of these numbers, they represent just the beginning. Real measure of success is the foundation that is laid for the future of OpenSearch's API development. Moving on to the epilogue, let's take a quick recap of the journey so far. The RFC to create the OpenSearch API specification repository was completed on 12th Feb 2022. This was quickly followed by the new repo creation. By June 2022, we had merged in the initial set of core APIs and handed over the report to the community. Then, over a period of 2 years, more definitions were steadily being added. In April 2024, the proposal to switch over to OpenAPI was accepted and implemented. And by June 2024, these specifications were ready to be consumed for client generation. That brings us to the current day. As we mentioned just now, we are at 65% coverage with client generation, documentation efforts being worked on, and moving steadily towards our North Star goal of server code generation using the models. Pranav?
Yeah. Now, remember I told you that this is also a story on how you can create your own RFC? Well, from what we did, this is what we learned. Firstly, do your groundwork. And before that, come up with a problem statement. It can be something as fundamental as creating open API definitions for for a product that has existed for tens of years, because that was a fundamental thing which did not exist. Post that, start with your groundwork. See what attempts took before you came up with the idea. For us, it was going through the code, documentation, and existing attempts. Check its feasibility and prove the utility to community. For us, it was creating API definitions and generating clients and documentation. Back up each and every line of your RFC with proof. Create a plan of action. And finally, iterate it with the community. You'll have to go for back and forth with the community, but the product which you're going to get, that is going to be refined. So what's the future? Well, other than the talks which you saw over here, the first one is documentation generation. If you go to the repository right now and look at the commits, you'll see that this is well underway. The North Star goal, which I believe would be there for this particular project, is to move OpenSearch to an API-first approach. You'll write your API, you'll generate the classes, and integrate that to OpenSearch itself. After that, you'll work on your development within OpenSearch. This is the RFC for that, and this is the issue for that. So I would recommend please put a +1 and your thoughts over there. And finally, why did we travel all the way from Bangalore to Amsterdam? We came here to solicit. Wait, sorry, that came out wrong. We came here to solicit your support. So go ahead, create that RFC, work on this repo, and if there's anything, please feel free to reach out to the community. Sachet, do you want to add anything?
No, we're good. Thanks.
Cool. So let's connect. If you're on LinkedIn, these are QRs, or you can just reach out to us. If you have any questions, we'll take them now. Thank you.
Thank you.
All right, terrific. Do we have some questions? There we go. Making me hustle.
Thank you. So thanks for the work. Quick question. So at the moment, if somebody is introducing a new API on OpenSearch core or plugin, is he or she somehow enforced to also define this API specification, or is not something yet done?
At least not yet, but we strongly recommend you do.
Okay, so it's still voluntary based.
Yeah, so like Pranav mentioned, right, our North Star is definitely generating server API code. And the first step towards that is basically ensuring all our APIs are on the repo, right?
So far, the maintainers are dropping a message onto the PR to add it to this repository. But yeah, would heavily recommend doing that.
Yeah, so it's still a catch-up game, and hopefully in the future
Yes.
it's going to be.
Yeah.
Good luck.
Thank you.
Yeah, thank you for covering the story of your journey here on developing this API. So at the current moment, are all the clients, many of the clients actually using this API for their this API spec for their code generation? Is that the state of affairs?
Yeah.
And how long will it take for OpenSearch itself to start utilizing, the API spec itself?
So that's a good question. So firstly, a huge shout out to the clients team. They adopted this and took it to the place where it is today. And client generation is happening via this. As for OpenSearch, I think it's about the priorities of the community. We saw some initial discussion on the issue, but so far, but it seems like it has weaned out a bit. So yeah, we need to restart that discussion, hoping for 4.0.
Just to add, I think there's a big challenge also making the server-side code generation using this. Like we said, right? Request response serialization, deserialization happens at different layers. So we have to really refactor a lot of things over there. We have to build a new code which will just use the POJOs created by the model instead of the ones which are being right now assumed to be there, right? So yeah, the work will be big, and community participation will be required for that.
Okay, and one other question was, I think along the way you found a lot of warts and things that you would have done differently. Are you planning to, streamline some of that, or is that something on the horizon that the API spec itself will be more consistent and more streamlined in the future?
I think since this is a product that is been there for a very long time, we really can't change much of this behavior. At least for the newer ones, we can enforce more standardized approaches. But at least the existing APIs have to be supported as it is.
Biggest issue that we saw was that it would not play by the HTTP standards that have been put. So for example, your GET API is going to have a payload. You will have the same parameter in your query and the JSON body as well. Other than that, use of untagged unions, where you would have a same parameter that could be either a string or an integer. Now, these workarounds have been manually created in the Open API definition. In case of Smithy, we use certain other workarounds, like creating a document type for a particular field.
Okay, thanks.
So you had a question about talking about the adoption, right? So we have been using the Open API specs, the doc team. So I handle the doc team for open source. And we have been extensively trying to push documentation into the API specs. With two reasons. Number one is it's easy for us to manage as versions change, which I think is one of the biggest challenges we have. The other part also is that we want to ensure that rather than having doc writers write from scratch and make typos, which we discovered recently, the API space makes it much easier for us to ensure that the content is close to what the API specs is. But like I said, right, if you enforce everything as best practices, nothing gets done, right? We want to make sure that people are willing to contribute. So as an example, in API specs, we don't enforce API specs, but we do try our level best to ensure that if a PR comes in and you're introducing new APIs, any user behavior, we do want to make sure that, so in our template for the PRs, we do have a section where it says a check mark that this requires documentation. And it automatically creates a doc issue, and we follow up that at a later point in time.
We got one more.
I'm from Uber, and we are working on the gRPC protobuf, so we are very heavily rely on the spec. So I think thanks for sharing the story. That's we also facing the similar challenge. So I have two questions. One is currently the high-level client doesn't cover. I think we have Java, but I don't think we have a Go. What's the plan and roadmap there? Since at Uber we have many users actually using the Go client. Second is, I think you briefly talk about the challenge about how to enforce or accuracy of the spec. So any idea that since during the process, so we are basically build the tooling from, generate the protobuf from the spec. And then during the implementation, we saw a lot of challenge that we need to fix the specs first, since we saw it's not aligned or correct based on the server POJO or whatever the implementation. So I'm wondering how we are plan to move forward with how to enforce the server and the correctness of the API itself. And also how we handling the versioning. I think currently the API spec have the beta version, but not the kind of formal production release version. So version in terms of what's the release, and the second question is about how we do, like, are we going to match the core version, like a 2.19 in the API spec, or we have like everything in the one place? So this is something would like to hear your thoughts.
So to start off with, like the Go client which you mentioned, again, basically we are, the current clients team who's managing the repo more actively might be more well-placed to answer it, but I see the Go client issue is already raised and there was some activity on that, but I see it's not happening right now. But yeah, we'll probably need to follow up on that the feature request. Regarding how do you ensure that it's matching the ground reality? So this is probably the testing framework which is being used right now, right? It will actually execute these tests against real OpenSearch servers. And the current testing framework which is there for the OpenAPI specification repo uses sort of a YAML-based test cases where you go and add your test case for every use case that you can think of. And we have been seeing maintainers adding comments on every PR saying that, can you please go and add a test for this in the specification repo? Right, but again, it's probably the best effort scenario where we try to add tests as best as we can.
Exactly. So one thing that we did while creating these particular specifications was go through multiple sort of specifications that were created, go through the documentation and the code itself. We found sometimes we would miss a field or two, and we would miss that within our integration test itself, because in case of OpenSearch, most of the fields are optional. So this is at a best guess approach, which we are taking right now. Now this issue would be completely removed once we go for a API first approach, where we define the API first, integrate that into OpenSearch, and then work forward. So till then, it's always going to be best guess. And I think finally it was the versioning, right?
Yeah.
So for Smithy, we handled it in a different manner.
So Smithy versioning was slightly different. It was date-based versioning.
Yeah.
But again, OpenAPI probably will have to. I think we can connect with the client's team who's maintaining it right now. So, yeah.
But I think it's going to be branch-based.
Yeah, mostly.
Terrific. All right. Any other questions?
All right, I think it's lunchtime. Thank you guys so much. It was super educational to me.
Thank you.
And yeah, I'm very excited that the docs could be auto-generated. I don't have to write documentation in 2 places. So thank you.
Thank you.